chemistry classes. We today will be discussing about the solid state of matter. Now, before describing the solid state of matter, we shall understand about a crystalline solid and an amorphous solid. Crystalline solids are those which have sharp edges and definite melting points, and the constituent particles are arranged in definite fashion over a long range. But in case of amorphous solids, they have no definite or sharp melting point. Their constituent particles are indiscriminately smeared throughout the substance and they have no sharp edge. So, you see that if we cleave the solid in different ways, we have a definite pattern of the particles, constituent particles. You see, round point, round point, round point. I have described the particle in this way, and if you cleave this vertically, we will found an arrangement, definite arrangement, and if we cleave angularly, we shall found another arrangement at the surface of the crystalline solid. Therefore, since the surface of the crystalline solid when cleaved through different directions are different, therefore it may be said or it is seen or observed that some physical properties like refractive indices, mechanical strain, thermal coefficient of expansion, conductivity, etc. differs or have different values or when measured along different directions. And this behavior is called anisotropy, and therefore the crystalline solids are called anisotropic in nature. Whereas in amorphous solids, the particles are indiscriminately smeared throughout the substance. That's why on whatever direction you cleave the amorphous solid, you will give a similar type of pattern, and so the values of different physical properties like refractive indices, mechanical strain, conductivity, etc. will have same values when measured along different directions. Therefore, and this phenomenon is called isotropicity or isotropy, and therefore amorphous solid is said to be isotropic in nature. Now guys, in a crystalline solid, there are constituted of some lattice. Now what do you mean by space lattice or crystal lattice? A space lattice or crystal lattice is an imaginary arrangement of points in the space where when the constituent particles are placed gives rise to the entire crystal. So we have drawn here an imaginary cage-like structure. This is called a lattice, and the dots are called lattice points. That is the points where the constituent particles are placed. And you see, the smallest part of this lattice is a small cube which when repeated along length, breadth and height gives rise to the entire lattice. So this shaded region is called an unit crystal. This is called a unit crystal. So a unit crystal is the smallest part of a lattice which when repeated along length, breadth and height gives rise to the entire crystal. And you see the constituent particles when placed into the lattice, those constituent particles are called basis or motif. Basis or motif. So we may say that lattice plus basis equals to a crystal. Pause. Now guys, sometimes crystalline solids can also be converted into amorphous solids. For example, quartz is a crystalline solid with SiO4 units. Quartz. This is a crystalline solid with SiO4 units. But when quartz is pulverized and melted and then followed by rapid cooling, it is converted into glass. But glass is not a crystalline solid, but it is an amorphous solid. It is found by the fact that glass has no sharp melting point. Glass melts over a wide range of temperature. For example, we see that glass panes of doors and windows of very old buildings generally becomes thicker at the edge and thin at the top. Why does it occur? Because on the irradiation of heat at the daytime, the glass melts slowly and runs downwards due to gravity, and this phenomena occurring for a long time makes the bottom end of the panes thicker and the top end thinner. So guys, you see glass is also called a highly viscous supercooled liquid. Glass can be also called a highly viscous supercooled liquid. So peach is melted over a wide range of temperature, and when it is cooled it becomes hard. Then even it is not a crystalline solid. It melts and it has some fluidity. So peach is also an amorphous solid. I already mentioned about the unit cell. I am drawing a unit cell separately here. You see, this is an unit cell. This is the smallest part or smallest unit of the lattice, and along these directions, you see I am drawing the directions, that is X, Y and Z direction. So there are six parameters. There are six parameters to describe a unit cell. Those are three edge lengths along X axis respectively A, Y axis B and Z axis C. There are three edge lengths along X, Y and Z axis A, B, C respectively, and the diagonal angle or interfacial angle alpha, beta and gamma respectively. Alpha, beta and gamma. So to describe a unit cell we need six parameters, three edge lengths along X, Y and Z axis A, B, C respectively, and three interfacial angles alpha, beta and gamma. With these six describers we can describe a unit cell, that what kind of cell it is. So guys, there are four types of unit cells. We are studying about cubic unit cells perfectly. So there are four types of cubic unit cells: simple or primitive, body-centered cubic, face-centered cubic or FCC, and end-centered cubic unit cell. So in simple or primitive unit cell, the constituent particles are at the 8 corners of the cube or of the unit cell. There are 8 corners of a cube and the particles are at the 8 corners of the unit cell. This is called a simple or primitive cubic unit crystal. Now, secondly, body-centered cubic unit cell. Along with the particles at the 8 corners, there are additional particle on the body diagonal and inside the unit cell, in this body-centered cubic unit cell or BCC unit cell. This is the body-centered unit cell. Now, face-centered unit cell. Along with 8 particles at 8 corners, there are 6 additional particles at each 6 faces of the cube, and this is called the face-centered unit cell. You see, along with the corner there are 8 particles, and at each face there are 6 particles. Okay? 6 particles. These are called face-centered cubic unit cell. In this face there is 1, in the upper face there is one particle at the center of the face, at the backward one this one, left side one this particle, at the down this particle, at the front this particle. Okay, there are 6 additional particles at each face of the cube. So it is face-centered cubic unit cell. And last of all, end-centered cubic unit cell. You see, end-centered. End-centered cubic unit cell possesses 8 constituent particles at 8 corners. In addition to 2 particles at the center of the faces of the opposite faces or parallel faces. You see, these are called end-centered cubic unit cell. There are 8 particles at each corners, 8 corners, and at the any two opposite face, either these two or these two, there are 2 particles at the center of each faces. This is called end-centered cubic unit cell. So we have learnt the 4 types of unit cells: simple or primitive unit cell, body-centered cubic unit cell, face-centered cubic unit cell, and end-centered cubic unit cell. Now, beside the unit cell, there are 7 crystal systems. Those are cubic, orthorhombic, hexagonal, rhombohedral, tetragonal, monoclinic, and triclinic. Now I have given the parameters of the unit cells. You see, for cubic unit cell, all the edge lengths are equal and all the angles are equal and equals to 90 degree. For orthorhombic, all the edge lengths are unequal and all the angles are equal and they are equals to 90 degree. For hexagonal, A equals to B, that is 2 edges are equal and the third edge is not equal to them, and alpha and beta is 20 degree but one angle is 120 degree. And for rhombohedral, all the edge lengths are equal, all the angles are all equal, but they are not equal to 90 degree but always less than 120 degree. On the other hand, in tetragonal, 2 edges are the same but the third one is unequal and all the angles are the same and equals to 90 degree. For monoclinic, all the edge lengths are unequal and 2 angles alpha and gamma are equals to 90 degree and beta not equals to 90 degree. And for triclinic, nothing is equal, edge lengths are unequal and all angles are unequal and they are not equals to 90 degree also. So there are 7 crystal systems: cubic, orthorhombic, hexagonal, rhombohedral, tetragonal, monoclinic, and triclinic. Now, by combination of 4 unit cells and 7 crystal systems, total 14 lattices have been proposed by Augustus Bravais, and these 14 lattices are called Bravais lattices. These 14 lattices are called Bravais lattices. Out of these 14 lattices, 7 are simple or primitive, 3 are body-centered, 2 are face-centered, and the rest 2 are end-centered. So there are 14 Bravais lattices. Out of them, 7 are simple or primitive, 3 are BCC body-centered, 2 are FCC or face-centered cubic, and 2 are end-centered cubic. Okay? Find out the effective number of particles in a unit cell. But before this, you see I have drawn a cube in the board. There are 8 corners of a cube, there are 6 faces and 12 edges. And first of all, we should find the effective number of particles in a simple or primitive cubic unit cell. A simple or primitive cubic unit cell has 8 particles in each corner. 8 corners and 8 particles are there. Now you see, these all 8 particles do not belong to the single cube, but each particles at the corner belongs to 8 other cubes. Therefore, the effective number of particles in a unit cell which is denoted by Z is given by, for simple cubic unit cell or primitive unit cell, Z is given by, you see, 8 particles and each has a share of 1 by 8 equals to 1. So, for a simple cubic unit cell, the effective number of particles is 1. And now, next one, in body-centered cubic unit cell or BCC. In body-centered cubic unit cell, there are 8 particles at the 8 corners. In addition, there are a particle at the center of the cube, that is at its body diagonal, which is shared by no other cubes. That's why for BCC, the effective number of particles Z equals to 8 into 1 by 8 again plus its own particle 1 equals to 1 plus 1 equals to 2. So, in body-centered cubic unit crystal, there are 2 effective number of particles. Now, next time, it is face-centered. In face-centered unit cell, you see, there are, in addition to 8 particles at 8 corners, there are 6 particles at each faces. So each face, particles at each face is shared by another cube or another unit cell. So each cube gets a share of half of the particle. Therefore, the effective number of particles for FCC or face-centered cubic is given by Z equals to 8 into 1 by 8 as previous one plus 6 faces into share half equals to 1 plus 3, which is equals to 4. So there are 4 effective number of particles in face-centered cubic unit cell. And last of all, end-centered cubic unit cell. For end-centered cubic unit cell, you see there are end-centered. Z equals to, so there are 8 particles at the 8 corners. So as previous, 8 into 1 by 8, the effective number, plus you see 2 faces. There are 2 particles in 2 opposite faces. Each particles has half share. So we could write 2 into 1 by 2, which gives 1 plus 1, again 2. So in the end-centered cubic unit cell, there are also 2 effective number of particles. So we summarize all the cases. For simple cubic unit cell, the effective number of particles equals to 1. For BCC, the effective number of particles is 2. For FCC or face-centered cubic, effective number of particles is 4. And for end-centered, effective number of particles is 2 again. So we should keep it in mind. We should keep it in mind for sake of problems that simple cubic unit cell possesses 1 effective number of particles. The effective number of particles in body-centered cubic unit cell is 2. The effective number of particles in face-centered cubic unit cell is 4. And the effective number of particles in the end-centered cubic unit cell is 2. Now, if the edge length of the cubic unit cell be A and the radius of each particle be R, then there are some relation. For simple cubic unit cell, R equals to A by 2. For body-centered cubic unit cell, R equals to root 3A by 4. For face-centered cubic unit cell R equals to A by 2 root 2. For end-centered cubic unit cell, it is not considered since it is not in our syllabus. So these three relations is to be kept in mind very carefully. And we have to write the packing fraction also. I am coming at the packing fraction in the next phase. So you should keep it in mind that for simple cubic unit cell, the effective number of particles is 1 and the radius of each particle is equal to edge length by 2, half of the edge length. In body-centered cubic unit cell, the effective number of particles is 2 and the radius is root 3a by 4. For FCC, Z equals to 4 and R equals to a by 2 root 2. This should be kept in mind. Packing fraction. Packing fraction. Packing fraction. PF. So packing fraction is actually defined by the volume or the fraction of volume occupied by the particles in a unit cell. So we may write that packing fraction equals to volume occupied by the particles in the unit cell divided by the total volume of the unit cell. Now this is a fraction, it may be multiplied by 100 to get packing fraction as percentage. Now you see, for simple cubic unit cell, the packing fraction is 52.4%. It is actually most loosely packed. And for face-centered cubic unit cell, the packing fraction is 74% and the rest vacant space. And for body-centered cubic unit cell, the packing fraction turns out to be 68%. So the densely packed, most densely packed unit cell is face-centered cubic unit cell, and least densely packed unit cell is simple or primitive cubic unit cell. We have to keep it in mind the packing fraction of all the three types of unit cells. We shall now find out the density, expression of density, or deduce the expression of density of a unit cell. So let we consider a unit cell of edge length A. Let the effective number of particles be Z. Let the molecular mass or atomic mass, whatever may be, molecular, molar or atomic or formula mass of each particle be m. Therefore, mass of each particle is this atomic, molar or formula mass by Avogadro number n suffix a. Now there are z number of particles, so total mass of the unit cell equals to z into m by Avogadro number, and the volume of the unit cell equals to edge length cube, a cube. Therefore, density rho is given by mass by volume, which becomes equals to Zm by Na into A cube. That is rho equals to Zm by Avogadro number into edge length cube. This is the final relation between density of the unit crystal, molecular mass, Avogadro number, edge length, and effective number of particles. So today, guys, up to this, we'll come back in the next day with closed pack structure, with metal deficiency defects and metal excess defects, that is crystal defects, and semiconduction of the solids. For till then, stay safe, stay home, and goodbye.